Hey everyone. Have you ever used an app and wondered why it feels lightning fast while another one just chugs along? A lot of the time, the secret sauce behind that speed is something called algorithm efficiency. Today, we're going to pull back the curtain and see exactly how developers measure what makes code good. Let's dive in.
So let's start with the big question. How do we even measure good code? I mean, is it really just about how fast it runs? Well, not exactly. Think about it. If we just used a stopwatch, my brand new laptop would always crush a 10-year-old computer. But that doesn't tell us which code is smarter, right? We need a better yardstick, something universal that works on any machine, anywhere. And that's where this idea of algorithm efficiency comes in. It's all about finding a way to judge performance that completely ignores the hardware specs or what programming language you're using. We do this with something called complexity analysis, which is just a fancy way of saying we're going to count the steps. And it really boils down to two main ideas. First up, and this is going to be our main focus, is time complexity. Now, this is super important. We're not talking about seconds or minutes here. Instead, we're literally counting the number of basic operations or steps a computer has to take. The real question we're always asking is, as our input size, let's call it n, gets bigger, how much does the step count grow? On the other side of the coin, you have space complexity. This one's all about memory. As you feed the algorithm more data, how much more RAM does it need to keep track of everything? It's definitely crucial, but just to keep things crystal clear today, we're going to park that idea and focus completely on time complexity. All right, enough theory. Let's see how this actually works in the real world. We're going to start with one of the most fundamental building blocks in all of programming, a simple loop. This is our perfect gateway to understanding what we call linear time. Take a look at this little algorithm here, getSum. Its job is super straightforward. You give it a list of n numbers, and it adds them all up for you. You see stuff like this everywhere. So let's actually roll up our sleeves and count exactly how many steps the computer has to perform to get this done. Okay, let's break this down line by line. First, setting sum equals 0. That's one step. Easy. Now, the for loop is a bit tricky. The condition gets checked for every single item, plus one final time when the loop fails and stops. That's why we have n plus 1. The addition inside the loop, that happens exactly n times. And finally, returning the result is one last step. Add all that up, and you get a grand total of 2n plus 3 steps. Now, 2n plus 3 is precise, but it's a little messy. This is where the magic of big O notation comes in. What we really care about is how the code behaves when n gets huge. I'm talking millions or even billions of items. And at that scale, that little plus 3 for setup, it's completely insignificant. Even the 2 in front of the n doesn't matter as much as the n itself. So we simplify. We drop the constants and focus only on the part that grows the fastest. Here, that's just n. And that gives us O of n, or linear time. The workload grows in a nice, predictable, straight line with the input. Simple enough, right? One loop, you get O of n. But what happens when we get a little more complex? What if we put a loop inside of another loop? This is where the performance cost can really start to skyrocket. And you can see exactly why on this slide. With that single loop on the left, you do n things. But with the nested loop on the right, for every single time the outer loop runs, the inner loop has to run a full n times again. You're doing n times n operations. That's n squared. A classic place you'd run into this is with something like matrix addition. If you want to calculate the new values, you pretty much have to use a nested loop structure. And if we counted every single step again, we'd get a big formula like this. 2n squared plus 2n plus 1. But look close. You see that powerful n squared term? That's the one that's going to take over. So you know the drill by now. We simplify it with big O. As n gets bigger and bigger, that n squared part is the only thing that really matters. We call this O of n squared, or quadratic time, and its growth curve is much, much steeper than linear. And you can probably guess the pattern. 3 nested loops, you'd get O of n cubed, or cubic time. Okay, so you're probably thinking, got it. 1 loop is O of n, 2 loops is O of n squared. Seems simple. But what if I told you there's a plot twist? It turns out not all loops are created equal. Instead of just inching forward one step at a time, what if an algorithm could take bigger and bigger leaps? Take a look at this loop. Notice anything different? The counter, I, doesn't just go up by 1. It doubles every single time. How do you think that changes things?
This shows it perfectly. The value of I just explodes. It goes 1, 2, 4, 8, 16. It reaches the target n incredibly fast. If n was 1,000,000, a normal I++ loop would take 1,000,000 steps. This loop, it gets there in about 20 steps. I mean, that is a night and day difference. This amazingly efficient behavior is called logarithmic time, or O log n. And let me tell you, this is one of the holy grails of algorithm design. When you're dealing with massive data sets, the amount of work barely even goes up as the data size explodes. It's incredibly powerful. So, we've seen linear time, quadratic time, and this super fast logarithmic time. Let's put them all together now, on one big chart, so we can really see how they stack up from fastest to slowest. And here it is, the complexity hierarchy. The absolute king is O of 1, constant time. It takes the same amount of time no matter how big the input is. Right below that is our hero, O of log n. Then comes our reliable friend, O of n, our simple loop. After that, performance starts to get more expensive with O of n squared and O of n cubed. And way down at the bottom, you have scary stuff like O of 2n, exponential time, which becomes basically unusable really fast. So, why does any of this matter? What's the big takeaway? It's that for any given problem, there are usually a bunch of different ways to solve it. Understanding this hierarchy helps you pick the right tool for the job. It's the key difference between writing code that just works and writing code that works beautifully and scales. And that's the final thought I want to leave you with. Every time you do a search, sort a music playlist, or just scroll through your social media feed, there are dozens of algorithms working behind the scenes. So now you can ask yourself, what's the hidden complexity, the invisible cost of all that code you use every single day? Thanks for watching.